Hello there, hello everybody, and welcome to another session of the Student Final Project presentations. Today we have one of our students who is going to be delivering and presenting to all of us his final project for the masterclass. This final project is going to be based on the Starbucks cafeteria, on the robot arm in this case. And yeah, I think we can get started already.
Yes, what I would like to say is that it's very interesting, this perspective, the way that our student, Leo Kim, he has achieved to make a robot grasp a cup and then put it on top of a second robot, on the specific holes that the robot has, so independently of the orientation and position of the second robot. For that, he will be using a perception, of course, to detect the object, the holes on the robot, and manage the whole thing based on that.
Yeah, and as always, if you have any question related to the project, you can write it down here in the chat, and we will try to make it to Leo, so that he can answer.
Yes, the questions will be at the end of his presentation. Excellent. Then, Leo, are you ready?
Get started? Hello, Leo. So, yeah, it's all yours. You can present your project to the audience.
Yes, I'm ready. Okay, share the screen. You see my screen? Okay.
Yes.
Yeah, we can see it.
Okay. Let's start it. That all people know coffee fills millions around the world, but engineers, good ideas always start with the cup of coffee. In the world of business, coffee is the handshake before the deal, and it's like a kind of shared ritual that sets the stage for successful partnership. For all of us, coffee is a promise that no matter the challenges ahead, we will face those challenges with renewed vigor. So what if we make coffee delivery automatically and establish the RoboCafé all around the world? Let's begin with the bits of interactive fun. Can anyone here guess what's the staggering figure of 2.5 billion minutes might representing the context of our daily lives?
Okay, let's wait for some seconds to allow the people on the streaming to get that and answer. Any ideas? Let's see.
Rodrigo says coffee is life.
Okay, but that's not the answer. 2.5 billion minutes. What could it be this?
Yes, what could it be?
2.5 million. Let's see, anybody in the chat has any solution? Alberto, what do you think?
That could be the total time that people dedicate in a day to drinking coffee in the world. I don't know. One guess.
It's a good guess. It's a super good guess. And what about...
Yes, it is.
It is?
Super good guess.
Okay.
No, it is not.
Oh,
okay.
But
okay.
it's close. It's close.
Go ahead.
we have one.
The average number of minutes needed to compile the raster
Workspace.
Okay. Good guys. Now, so hold on to those thoughts and let's reveal the mystery. It is the time we can save in one day if RoboCafé is established globally. Imagine this, an astounding 2.5 billion minutes per day could be repurposed from coffee runs to productive work. So here is another intriguing figure, 48.8 billion minutes. Any ideas what this number could signify? Think big. Okay. Technology changed a lot of things.
Okay, thinking big. Then let me guess myself this here a bit before anybody in the chat says. So thinking big, that could be, I don't know, the amount of time of the...
Productive work.
Productive.
Okay, for maybe is the amount of minutes that waiters are dedicating to serve
That is the good sex, but you should think big, more bigger.
Okay, in the world. Okay, bigger than is the
In the solar system.
no idea.
Okay.
I have no idea.
Okay, let's review this figure.
Yes.
It is the cumulative time Google invests over 2 decades to become a titan of industry today. So now envision this. With the world interconnected by automatic coffee delivery, we are not just cutting down on coffee runs. We are potentially accelerating the next Google-sized innovation. Every minute we set could be the minute spent on the next big breakthrough. So now let's shift from the imagination to reality and see how RoboCafé in action through the simulation, showcasing the future of automatic efficiency. This is the web page for my web page and for coffee orders. Once an order is placed, our system perception algorithm will spring into action, locating the property slot for cups. Now watch closely. Yes, it's identified the targets. Next, we will initialize the delivery sequence with 4 coffees order. The system will complete 4 cycles. This video is organized to 4 parts. Feedback. This area provides the real-time updates the robot arms movement, and the result will report if the task is complete. In the lower left corner, we have the gazebo simulation environment work. To its right-hand side is the RV setup displaying the movie's configuration. During this demo, you will notice the cup will be removed. Remove it from the simulation. This is the efficiency measure to conserve the result and maintain the gazebo performance. As we progress, you can see the feedback is keep output and update. And final, the result will come out to succeed. So now let's dig into the core architecture of our system. First, we take a web order for coffee and transmit into our Docker container. Our system will leverage the PCL library to precisely compute the position for the cup and from the data of camera perception. Then using the movie tool to plan the trajectory. Finally, the arm will deliver the coffee to the barista robots. So let's go deeper into each process. Let's unfold the components of our system. First, we start from the flowchart. In the flowchart, the web page has 4 main jobs. ROS bridge connection is sent the service required, and subscribe the feedback and subscribe the results. The ROS bridge server is used to bridge the system and web page. Upon receiving a service request, the system will spring into action, triggering a cascade event. It will start the movie to action, which in turn prompts the perception system to determine the coffee cup position of the coffee pot position. As part of the movie 2 process, it will publish the feedback topic and result topic. Now, in here, someone might wonder why I opt for surveys and topics rather than using the actions directly in the web page. The reason is practicality. It's simple, because the current version of the ROS bridge server I use in our system has just introduced the action functionality. They just introduce it. So, which is unfortunately, it has a lot of bugs and unreliable to use. So in response, we utilize the service and topic as substitution, which is more robust now. So next, we transition to the web page interface. This is the entry point where coffee orders are placed and initiated. Hold on.
Hello, we can see your screen.
Yes, how about now?
Yes.
Yeah.
Now
Yeah,
we
yeah.
can see your
Yes.
web page.
Yes. The web page, this is the home page, and we explored our menu. You can see our menu has 4 types of coffee: cappuccino, americano, latte, mocha. Although we cannot select the coffee here. And next is the introduction about the RoboCafé, and I post the GIF here to see the simulation of the whole process. Next, we can order the coffee to click the button, then can connect by the Ross bridge and send a go here. Let's snap back to our PowerPoint. Okay. Next, let's move forward to the perception. In the perception processing, we have 3 main parts: segmentation, extraction and reorder, projection, and convex full. We start from segmentation. Now you can see that is the point cloud we received originally. Here, since we only want to the parts of the whole, so we segment the whole from the original point cloud. The above is the plate, and the below is the whole cloud we want. Next, extraction and reorder. In order to note each whole position, we have to extract each whole cluster from whole cloud we just obtained. For the consistency and security of the robot arm movement, it is crucial to determine the distance from each whole cluster to the robot's best link. So to add in this, the whole cluster are reordered. They are colored for clarified. The further the cluster is from the best link, the darker its color. So you can see the farthest one is the most darker one. Next is the projection and convex full. Finally, once each whole cloud is isolated, we project it onto the plane for ease of analysis. This projection simplifies our mathematical calculation, aligns the data within the plane. You can see the red dots, our laser to show. Next, we employ the convex full functionality within the PCL library. These powerful tools allow us to extract the convex outline of each whole cloud. It is a crucial step in accurately defining the center of our subsequent the computational task. In addition, you can see the green point cloud here is the initial position of our arm to move. This is the insurance to avoid arm to collide in the gazebo. The gazebo simulation does not always work expectedly, so we need to set it for insurance. So next, we have acquired the desired point cloud for the perception systems. So it is time to enter the mathematical realm. You can see the first line is the equation of the ideal circle. I leverage it as our foundational formula, this equation. Then we expanded the equation and substitute the variable to A equal to XC, B equal to YC, and C equal r squared minus xc squared minus yc squared. Then, in order to efficiently address the challenge of thousands of points, I transformed the expanded equation into the matrix form. This step collapses our problem into compact linear algebraic equation A dot x equal b. With this equation in matrix form, we can apply the least square approximation to solve the x. So in conclusion, that by solving this, we are able to accurately calculate the hole center, SC and YC, and the radius for each hole. Also, when we derive the center of each hole, I use the RV marker to mark the center with yellow dots here, and circumferences to the blue line as the debug tool. So finally, with the coordinates in hands, let's move to the movie 2. To ensure the robotic arms operate safely during the coffee delivery process, it is important to configure the movie 2 scene to prevent any potential collision. I separate it to two parts. Firstly, we establish the static elements of the scene, which includes the coffee machine, the clamp, the bartender, and the wall. It defines the boundaries the robot operates. Secondly, we account for the dynamic elements, the barista robots, and the coffee. This aspects are based on the perceptions of the object position. But notice that the initial position of the cup is assumed unchanged throughout this process. So in this slide,
No worries. We can see.
In this slide, we recall the arm trajectory. Initially, the gripper will close to secure its grip and transition progress and take the cup and approach to the hole and retrieve from the hole. Just recall the arm trajectory move. Then, the move it to cell trajectory we have recorded. So now, we describe it in the description. The orange square represents the gripper and the white rectangle represents the manipulator. Just like what we recorded in the videos, it closed the gripper first and transition to the progress position. Following this, it's open the gripper and approach to the coffee. Post-approach, it attach the coffee collection and then pick the coffee up. The spatial is here. How the arm navigates to the hole position. Let's see. I integrate waypoint constraints for precise navigation to the hole position instead of just utilizing the rotation degree best method. That's for short in accuracy for any vector position. So on the left-hand side, you can see that is the movie constraint message. I use the orientation constraint to regulate the end effector's links orientation. On the right-hand side is the step code I used to set up the orientation constraints. Let's see the result of this setting. You can see it directly moved to the initial hole position and to correct position. Next. After moving to the hold, the arm will approach to the hole and release the coffee, finally retrieve from the hole. So now that's the video in the real lab. The whole process sequence is the same with the simulation. We send the request in the web page, then the perception and mathematical process will begin and return the position. Following this, the arm began to move. Figure continuously showing the state of the arm. And move another one. Open the grid. Now it's third cup. Yes, the last one. Yes, you can see the result shows succeed. So what will happen if we change the orientation of barista robot? Let's see in the real lab.
Okay, so we are going to see a real time demo now, Leo.
Yes.
Okay.
Real time demo.
Okay.
Now
We can see your desktop. Now we can see you.
Another screen.
Okay.
Okay, now we can see the project. Yes.
So what are you doing right now?
I'm connecting the robot.
From your what? From your project?
Yes, from my project.
Okay. Yeah, so now Leo is connecting live from Taiwan to the robot here in Barcelona, so the cafeteria, and then he's going to execute live his code, and we are going to see through a camera the results in real time. He's getting connected.
Okay.
Okay. So I need someone to push the coffee in the initial position continuously.
Yes. So Rodrigo is there.
He's there.
So we should see him on the camera, and then he's going to be put in different cups. Okay, so we can see the robot filling all the holes of the barista robot, of the delivery robot. Mm-hmm. So now what are you launching in all those things?
Yes, I'm launching the old thing, all of the perception action, the movie actions, and the service assets, which is for the web page to use.
Mm-hmm. Okay, let's see. We have one. We can see on the camera that we have one of the cups there, and also I saw the feet of Rodrigo around there and the shadow. Yes, so he is there, ready to help you to put another cup.
Okay.
Great.
Now order the coffee.
Yes. So yeah. So now we are ready. Okay. So the system is ready for you. So go ahead.
Yes. Okay. Now we connect the rock bridge and send the amounts of the coffee, 4 cups of coffee we want.
Okay.
now. So now it's showing the perception, finding the place. Okay. Yes, see, it's closing the gripper into the initial position.
So this position of the cup of the initial position, this is a fixed position, right?
Yes, it's the fixed position. Then it will move to the initial hole and approach, release, and
Excellent.
retrieve.
Then Rodrigo, go ahead. Put another one. Okay, so yeah, so I think that we got confused with the instructions. So Rodrigo took the first one and put it back. Yeah, I wanted to show the audience that it fills all the holes. There, Alberto comes to the rescue. Yes. So now the robot is grasping the second one, and then what is going to happen?
Yes, it's going to deliver the coffee to the second farther hole.
Okay.
Yeah, release the seed.
Yes.
Go to the next one.
Okay, yeah, and then a third cup is being put in place by, I don't know if Alberto or Rodrigo, somebody. Then want to clarify that the position from grasping, it's fixed because that was the constraint of your project. So we expect in this project that there is a cup. Somebody put a cup there every time. Rodrigo is there. Okay, so now he's going to put it into another of the empty holes, right?
Yes. So seed and the final cups.
And then the final one. Let's see. So the center of the holes, it is computed once the whole process starts or every time that you are going to serve a cup?
Sorry?
When is the center? Okay, let's see. This one is the final one.
Yes, final one.
Completed. Excellent. Excellent.
Wait, but we wanted to try something here.
Yes. What is?
Yes.
Okay, so that is still to be tested. So
Okay, what is this? What we want
it was to rotate the robot and see what happens, right?
Yes, exactly. So what if Rodrigo removes or Alberto, one removes the cups now, and then we rotate the position so we can show to the audience that you are actually computing all these data and it's not in a fixed position of the robot. So now Alberto is doing this. We can see on the camera, and he's rotating some position. Yeah, so...
Okay.
Yeah. So can you launch it again? Can you request again?
Yes, of course. But we need to, because the latency of the camera, so we need to check if it's updated.
Ah, yes, that is right. Yes, very good point. This is one of the errors that we discovered, right?
Yeah. Yes.
By testing, yes. Yeah, so take into account that this is a very complex system that is made, it's done in the cloud and remotely. So Leo is in Taiwan, then this project is in the cloud, which is located in Japan, actually. And then the lab is in Barcelona. So all those connections are being established right now.
Yes, so it sometimes will have the latency problems.
And then we didn't get the point cloud properly updated. I think it's correct.
I think it's updated now.
Yes.
Yeah.
Yes. Okay. Okay. Let's send another request.
By using the web page, right?
Yes, using the web page and connect again, then send a go.
Okay.
Let's see. Yes, it's closing the gripper. Move to the cup.
The handsome man on the image is Rodrigo, one of our members of the construct.
Oh no.
Okay, so it was not updated in the
Yes,
code.
it's not. Yes, it's not updated.
Yes. So that's the mistake that we got before. Okay.
Shall we try to relaunch it?
Yes.
Yes, relaunch it. I need to relaunch it again.
So we are going to remove the glass, the cup, sorry, in the robot that was wrongly placed. And then we are going to relaunch everything. So we actually know that it's getting the latest point cloud. That suggests to me that the problem of the point cloud not being updated is not because of the latency, it's because something in the code that is kind of not refreshing.
Yes.
The variable,
yes.
something like that. So now if you launch it again, then it's going to work because everything starts from fresh.
Yes, I think so.
Yes. Yeah. Okay. So those are small things that happen in a complex project.
It's preset again.
Okay.
Let's see what happened this time.
Yes. There it goes. There he goes.
Yeah, I think now it's looking better, yeah.
Yes, it's going there.
Yes.
Yes, success. Yeah, so that means that there is some problem in the in the buffer or the variable that captures the point cloud.
Yes.
Okay. Can you explain where is located the point cloud device that allows you to do the perception? Where is it in this image? What is the camera?
Oh, yes. The camera, the perception we receive is from this camera. And it's set up properly to get while we get the point clouds from the camera, we met a lot of problems. Sometimes it's the angle, sometimes it's the TF frame setup. It is all the key points for me to get the accurate position of the hole. Yes.
And then there is a transform between this camera and which other frame? Oh,
yes. This transform using this camera using the D415 camera optical frames. So we need to transform it to reference it to the best link. Then we can calculate the data points from Bastlink. The reference is we transformed the camera frames to the robot's brain. Then we can easily to calculate the points X, Y, Z according to the Bastlink.
Exactly.
It will makes the poor calculation more simplified.
Okay, excellent. And now we go to the final cup. There it goes.
All right.
Awesome. Rodrigo approves also. Excellent. Excellent. Awesome. Yes, and we tested with different positions and other rotations, and then it's also working. Apart from that error of the refreshing of the point cloud. So apart from that, then it works on different positions. So why are we restricted on positions there of the robot, of the barista robot, the delivery robot? Why can we not put it in any place there? So it's restricted in an area. Why is that? You know what I mean? My question?
Restrict the barista robot?
Yes. So we cannot put it anywhere on this picture, right?
Oh, yes.
So
yes,
why not?
Yes, that is another issue we met before. The main issue we met is it's easy because the arm cannot reach anywhere we want.
Exactly.
So we only have the boundary. We have the boundary to reach. The arm can reach. So we need to be careful to this problem. If we want the barista to the coffee position and to receive the coffee, it will be the really important issue. But actually, if we set up the navigation for a barista robot, the deviation will not that big.
Exactly.
Yes. So it is acceptable for us to use the arm.
Exactly. Yes. Okay. Correct. Excellent. Excellent. Then now let's go to some
Q&A?
questions. Yes.
Yeah. So if you want, you can now stop sharing your screen, Leo. And if you want to show something in one of your answers, you can go back and share your screen. Okay. So here we have Leo, and then we have received some questions already from the audience. There is one here which I think is interesting, which is, what would happen if we change the current robot, which is a UR3E, as you said, for another robot? How would that affect your program? Would you need to change something? No?
Change barista?
No, the ARM. What would happen if we want to do your project, to replicate your project, but using another ARM? What would happen?
I think actually that is not a big issue, because if you have the description set up, I mean the URDF description set up well, and yes, and also the movie tool supports, because I use the movies as the interface to use. So if the movie tool support this arm, it should be okay. And because, yes, the most important thing is the URDF setup. If the end effector set up correctly, it will not be the problem.
Okay, yeah. So basically, what we would have to change is the movie to package, right? For the new ARM and the new URDF. Yeah. Okay, so
another question. So let me ask you a question.
that is also good.
So that is a question that I asked you before, but we got involved into the problem of the point cloud not being updated. So you show us about the computing of the center of the holes, right? You show us, and you were computing the center, and you use this position to move the arm into the with the cup into that position, into that center, right? That's your program. Then is this center is computed once? So you do the perception once, compute this, and you never compute it again until it finishes the whole process? Or are you computing this regularly with a frequency or something?
No, actually, I collect 10 times for insurance, 10 times of the point cloud to make sure the point cloud is robust, and I only calculate once.
Okay, at the beginning. And then for that, you use a library that is computing this circle fitting model, right? In order to do that from the point cloud. But
no, actually, it is not the public library. I just use the mathematical method to solve the equation.
Yeah, but did you implement my question is, which library are you using for that? Are you computing this in your program so directly? You are computing the matrices?
Yes.
So you are using raw C++ vectors directly?
Yes. Use the C++. The matrix transforms, actually, the inverse matrix transform to calculate the results.
Okay. Yes. Okay. I thought that you were using a special library or something. Okay. Great.
Well, the agent library.
Okay. Yes. Okay.
Yes.
Agent library.
I think you are asking this.
Yes. Exactly. So I was supposing that you were using this agent library.
Yes.
But then you said that, and then I thought I was watching yourself doing the program of with a vector of data, and then doing the computation between matrices and making it so. Okay, that makes more sense. Okay. Excellent.
Yes, I use the agent library to calculate it.
Okay, yeah, so here we have another question by Girish. He says, can the robot put the coffee cup in any requested hole? Or is it always all the 4 holes in the same sequence? So.
Any put the coffee in any requested hole. Actually, I order the coffee sequence by its distance to the arm base link. So for example, if you order 2 cups, it will put the coffee into the more farthest hole, then the second one, the third one, and the final one. Mm-hmm. Yes, if the customer have these requirements, like if they want to put it to the specific place, it is available. It is okay. I will set the order of the sequence is because sometimes in a gazebo, the arm will not work expectedly. So I need to fix this sequence to make sure it can work perfectly.
And another question from Andres Leonardo. He says that if the robot barista, the delivery robot, were taller or shorter, does the program consider this?
Let me think. In my current version, it cannot, but it is not a big issue because I can use the point called Z if the depth camera perceive the points in the correct position. I can use it as the Z direction to approach to the hole, for the arm to approach the hole. It will not be the big issue to solve, I think.
So right now you are using a hard-coded value for the Z, but you could change that to use a variable, right?
Yes, it can be changed.
Okay. Then let me see here, more questions. So,
Previous customer.
So let me see here. Oh yes, I had this question about the colors of the detected holes, but you already answered, right? Because the colors are indicating, what are indicating the colors of the holes? You show us different grades of blue for each hole.
Yes.
And this is indicating the distance, right?
Yes, it indicates if the color is darker, it means it's more further from the best link. The cluster is more further from the best link.
Okay. And then you will use this color. Well, the color is for us, for understand, right? But you will use this as an order for serving the cups, right?
Yes, exactly.
Okay.
And I see the question, would you get an error of something if there is the cup in the hole already from the previous customer? Oh,
yeah, from Rodrigo.
That is the really interesting problems that actually I can solve this problem in the simulation. I can calculate while in my code, I can run the perception to get the correct cup precision in the simulation, but I cannot get the correct precision in the real lab because I don't know if it is the camera problems. It's the point clouds gets from the camera will collapse while the cup is putting on the robots. It cannot calculate the shadow of the cup. So it can only knows the depth of the front side of the cup. It cannot get the back side, the back side of the cups. So that is the reason I cannot get correctly the cup position in the real lab. So I do not implement in this presentation.
Okay. Yes, but then how would you solve this?
Oh, actually, I have an ideas. We can solve this by using the color. If we have the really distinguishable color, like if the robot is white and the coffee puck the coffee is black or something, then I can filter the robots out and use the same way I calculate the hole to calculate the cup.
Okay. And what about adding more perception?
Yes, that is another option.
How would you add this perception so that it's useful for you?
Actually, I'm not really professional in this room because I'm not sure if any like we're using the camera now. How about using the other service to find the perception of the coffee? I don't know what will happen. So I'm not sure how to set it well, but if the more correctly way is to set the camera on the top of the robot is the more fastest way, I think. Since you can know the depth directly, it's not by the computation.
Okay, and then let me suggest you another way, and then tell me what you think. So what about if you have a model of the cups that are in the used in the cafeteria. So if you have a model of the cup, and you know the shape, the exact shape. For example, I have this one now, but here, this one. So you have this, and you know that a hole is occupied, then you know that it's occupied by this. Then how would that help you solve the problem?
Yes, I think that is the common way to separate, to find the cup. I think it might well, but I'm not sure if I using the PCL, the point cloud, to deal with it. What is available or something? I'm not sure. So it need to be experiments.
Okay. Okay. Let me see. More questions?
We have one last question, I think,
Okay.
from Ritwik. So can you explain how are you computing the circle boundaries of the holes? I suppose he refers to that.
Are you checking the pixel change?
The circle
fix?
boundary.
Yes, I see that question. I see the question. How do you compute the circle boundary? You mean that question? Are you checking for pixel change to fix the circle? Actually, it's the mathematical. I can show. In this page. Okay, now you can see the screen. Can you see the screen?
Yes.
Yes. Actually, I calculate the border. I calculate how to compute the circle boundary. You means the boundary is in the marker? Is it?
I think
I guess so. Yes.
Yeah, I understand that. The blue circle.
Oh, the blue. Yes, it's just it's just from the radius and the centers. We have the center, so and the radius, so we can easily to have the circumference of the hole. I calculate it from this.
And
did I answer the question?
So in another image, not the one for the marker, but in previous images, there are also some other circles which are computed from the point cloud. Not here, but before.
And that one's also from the point cloud.
Which one you mean?
Let's go back. Those are point cloud too.
Those are markers, I think.
This one.
Convex wall, you mean? This one?
The blue ones on the right side.
Yeah.
Right bottom.
Oh.
The blue and green.
So this slide is correct?
Yes.
It's correct.
Yeah, so those circles, the boundary, so how do you decide what is the limit, the radius, let's say?
Oh. So I guess he is asking how the convex force works.
Yeah.
I just use the PCL library. It's called the convex wall, and it will extract the convex outlines of each whole cloud. Then originally it should be look like this one. It will project. I project it to the bottom, and I only want its outliers of the point clouds.
Okay.
So I use the convex tool to get this border. Then I can calculate it perfectly because it has thousands of clouds there.
Yeah. So basically,
thousands of points there.
Yeah, it's not based in the pixel color. I think it says. So basically, it's you detect the change in the depth, right? In the plane, let's say.
So yeah, so the problem is how to make sense, how to make those circle kind of circle that you are pointing right now with your cursor, how to get to that from getting what is on top left. So from top left, you have all these point cloud with different colors. Top left of this image. Top left.
Oh yes,
There's
top
one.
left.
Yeah, you have this, but how that translates into the bottom right image of this slide. Bottom right.
Oh yes, that I can explain this again. This actually first I project the full point cloud. Oh no, I extract. I need to back to the previous slide. The first thing after the segmentation is to extract each point cloud out from this point cloud. So now I have 4 whole point clouds.
Okay.
And I reorder it. So I know it have the sequence. And then I project it to the bottom of the whole point cloud.
I see.
I project it here. So all of the cloud is within the plane.
The plane of the barista robot.
Yes.
Of the top
the
of the barista robot.
Actually, I don't care about the Z direction of the point cloud here. So next, after I project it on the plane, I use the convex flow tool to get the border of the circle. Since I only want the border, because why I need this? Why someone might have some ideas that maybe we could have the average of the circle, all of the points, not only the border. I mean, before I use the convex tool, it's like this.
Yes.
Why I directly use this and use the average to calculate the points and calculate its
the
XY.
Center. Yeah, the center of each one.
Because it is the angle, it is the problem of the angle of the camera. The camera is look the hole in the right hand side, so it has some depth angle. It cannot get some point clouds. So the center, if I use the average to calculate the center, it will have an offset to another direction.
That's
to this direction.
A very good point. Yes.
Yes, it might be here.
Yeah.
So I only want the border of the circle.
I see. Makes sense.
Okay,
Excellent.
so I think we can leave it here.
Yeah, you have answered a lot of questions already.
So
and we can see that you know your craft. So wanted to comment about your presentation. So then first a couple of things, because I like it very much. So I want you to know that. So first of all, I like your solution for the switching to the topics of the feedback for the web page. So on the web page that you have created, you are showing the feedback about the results, right? What is happening with the robot arm at any point in time. And for that, you could have used the action servers. But you mentioned about the problems of the action server in the ROS bridge. And then for that, you decided to go into the topics. That's very intelligent. And that shows that when there is a problem, because the technologies we think, like in the movies, right? We think in the movies, oh, yeah, you connect like this and then you get it. But when you do it in reality, this cable is broken. Then the version of the library of this computer is different from the other one, so they cannot talk. That's the reality. And then you have to be clever to figure out new solutions on the spot, all right? And then that's a very good one. So
Yeah, so maybe you could have spent 1 week trying to make the action bridge work. But instead of that, why just not use a service which is working, right?
Topic.
No, service actually it is, right? Or
Is it service? No.
Yes, both of service and topic.
both?
Okay.
I use the topic for the feedback and result, and the service for the request.
For the request. Okay. And then also wanted to say about the whole style of the web page, which is awesome. You even created this icon that for logo for this that you have on the background. Yes. So can you tell us about this? This is very cool. How did you create that?
The technology changed a lot of things.
Okay.
I use the models AI photo generator to create this image.
Okay, then it's very cool. Then congratulations for your presentation, for your full project, and for all the details that you have put into your project. It's awesome presentation. Yeah. Congratulations.
Well done, and congratulations also for finishing the masterclass. It's been a long journey, but you have reached the end. Yeah.
Yeah.
Well, still maybe internship. We still have to talk.
Okay, we'll talk next week about that.
Okay.
Excellent.
All right, Leo.
Thanks. Special thanks to Alberto and Ricardo. They always accompany me for a long time for the experiments, and everyone can see they are familiar with my project. That is because they are both involved in these projects for the experiments. And special thanks to Miguel Rodrigo for my asking question. And the final one, the assistant Garish, is really efficient, really quick response for everything. He's really hardworking. Thanks.
Yeah.
Thanks him.
He's there on the chat, so he's going to thank your words for sure.
Yes, a lot of people are here showing love. It appears like love on there.
All right, Leo, so many thanks, and then we will see all of you in the next student presentations, which is going to be more or less in 1 month, with more cool projects. So, yeah, let's leave it here. Thanks again, and yeah.
Thanks.
Thank you very much.
See you around. Bye-bye.
Bye-bye.
Thank you. Bye-bye.